Good afternoon, one and all present here. On behalf of management, principal, HOD, and faculty member of Mohammed Sathak KJ College of Engineering, I welcome you all for the first day of International FDP on recent trends in drafting and mathematical modeling and its application. This topic is specifically chosen for the reason that it is much relevant in the present scenario applicable in various job studies. Graph theory is a mathematical concept that describes the relationship between objects in a network. Graphs are used in many areas of mathematics, computer science, and engineering. In addition, they can be used to model many real-time situations, including social and communication networks. We are very happy to conduct one week FDP on such a significant topic for our faculty members of engineering and technology across different countries. Hope this FDP program provides depth exposure in the field. Now I invite Dr. HOD Maths for the welcome address.
Good afternoon all. This is Dr. A. Ammukutsiya, HOD SNS Department, Mohammed Sathak AJ College of Engineering. On behalf of the management, principal and staff, I am happy to welcome our resource person, Dr. Mohammed Ali Ahmed, Department of Mathematics, College of Education for Pure Sciences, Al-Haitham, University of Baghdad, as a resource person on the topic graph theory and labeling with application. I welcome you, sir. Sir, thank you so much for accepting our invitation and being our resource person today. Eagerly waiting for your presentation, sir. And
thank you, madam.
Thank you. And also, I'm happy to welcome all other participants from various colleges. Welcome you all, ma'am and sir. Hope you all have a wonderful session today. Without further ado, let me open this session and over to Sudha ma'am. Thank you.
Thank you, madam.
Thank you, ma'am. I take this opportunity to introduce speaker for day one of International FDP. My hearty welcome to Dr. Mohammed Ali Ahmed, Department of Mathematics, College of Education for Pure Science, University of Baghdad, Iraq. He received his doctorate in 2018 at Anna University, Chennai. His area of specialization is graph theory and labeling. To his credit, he has more than 20 publications in both national and international journals. He has also participated in more than 13 international and national conferences and 12 international and national workshops. Now I invite Dr. Mohammed Ali Ahmed to take over the session. Thank you, sir. The session is over to you, sir.
Thank you. Good afternoon, one and all. I'm very happy to speak with my second family, the Indian family. I love India and especially Chennai. I finished my PhD at Anna University, Chennai in 2017. I was in Chennai from 2013 till 2017. I miss everybody in Chennai, and I hope one day I will visit it again. Now I share my talk. Is the screen available? Okay. Okay. My talk is graph theory and labeling with application. My talk will be divided into two parts. The first part is graph theory, and the second part is labeling with application. We will give a small introduction about the about the graph theory. Small idea about the graph theory for the second part. Then for the first part, and on the second part, title labeling with application. We will go for the labeling and give a small application for the labeling. Let us first give a general idea about the graph theory and some of its application. The graph theory is a branch of mathematics deal with the points connected by lines. These points are called vertices or nodes, and the line are called edges. Birth of graph theory started in a paper presented on 26 August 1735 and published later in 1736. It's regarding the first paper in the history of graph theory by the Swiss mathematician Euler. The paper deals with the problem called Congress bridge problem, 7-bridge problem. What is the vertices and edges? Hello? Everything is okay?
Yes, sir. Everything is okay.
Okay, sorry. Vertices and edges. What are the vertices? The vertices dependent on our problem. The vertices may be the city, maybe the house, maybe the computer, maybe the person, dependent on what we are problem. So, what are the edges? The edges also dependent what are considered the vertices. Suppose we are consider the vertices as a city, then the bridge connected to city will be the edge. Suppose we are consider a vertex as a building or two buildings, then the edge or now the bridge connected these two buildings become an edge. And suppose we consider a computer as a vertex, then the line connected these two computers will be the edge. And other also bridge and the connection, if we consider the network, the connection between any two persons will be the edge. What is a graph? A graph denoted as set of G equal V and E. V of G is the set of vertices and E of G is a set of edges. Now let's take idea about some kind of a graph, simple graph. Here, this is a bipartite graph, cycle graph, complete graph K4, path graph, and cycle C5. All those are simple graphs. Now we have two special cases of a graph. The one case is called multiple edges. The second one is called loops. We need to take idea about why sometimes we use multiple edge and loop. If we have connection already between 2 points, why or what is the reason to use multiple edge? Look at this map of road. A, B, C, D, all this is cities, different cities. The cars come from A, B, C, D, all going to E through this edge. So we have 4 cities, A, B, C, D, and D, and all the car want to go to the city E must through this edge or this road. So this road have too much traffic. The timing for waiting on this road will be maybe, for example, 30 minutes. Afternoon crowded, so the time here, waiting time is 30 minutes. We want to solve this problem. We want to solve this issue. We have traffic time here. Now we will do multiple edge. After doing multiple edge, we reduce the timing, waiting time, we reduce it because instead of one road, we have 2 roads connect the city D and A. Suppose we want to reduce the time again. We will do again multiple edge. Now the time is reduced too much. Suppose the initial time for waiting 30 minutes now become 10 minutes. So for that reason, sometimes we use multiple edge. Or for another idea for multiple edge, maybe this is 2 lines with different speed. This is highway and this is normal. If you go for highway, you need to pay some fare. Here is a free. For that reason, sometimes we use multiple edge. What about loop? Where can we use loop? Suppose we want to do parking on the city F. So now we use loop. This is loop. We are making as a parking on the city F. Let us take a simple application of graphs. Take idea about how can make application of graph. Suppose we have set of numbers A. This set of numbers include 10 numbers, 1, 2, extra 10. This is any set of number. And we have a relation for those number. For every two different number, xy belong to the set A, and x is not equal y. X have relation with the y if and only if x plus y is odd. So the relation between two numbers is if they have relation if x plus y is odd. Otherwise, there is no relation between them. So if we consider any number as a vertex, and if this relation is true, they have edge between them, we can go for this graph. Look at this graph. Now here, this is complete bipartite graph. K 5, 5. This represents this relation. This graph represents this relation. X have relation with y if and only if x plus y is odd. 1 plus 2 is odd, 1 plus 4 is odd, 1 plus 6 plus 8 plus 10. And for any two number, if x plus y is even, there is no edge between them. Now this is for this relation, if x plus y is odd, the relation gives us a connected graph. What about another case? Suppose we want the relation x plus y is even. What's the graph we will got? See here. If x plus y is even, we will get this two graph. Connected, disconnected graph. In the case x plus y is odd, we are got connected graph. In this case, x plus y is even, we get disconnected graph. Here, any two number consider as a vertex, and there is edge between them if x plus y is even. If this number plus this number is even, there is then there is edge between them. Otherwise, there is no edge between them. Some application of graph theory in our daily life. Internet. One of the largest graph in our life is the internet. How it will work? In web page search like Google's, website and page are linked in a graph, which help to rank website and make it possible for Google to display the best result at the top. In social media like Facebook, WhatsApp, and others, the users, people are represented by the vertices, and any connection between the users, such as followers and friendship, are represented by the edges. Networks. For airline to connect countless cities in the most efficient way. For road network to develop the intelligent transportation systems. Other applications, traffic light, solving crime, design of computer chips, and map coloring. Now we will go to the second part of our talk, which is a graph labeling. One of the most interesting problems in area of graph theory is a graph labeling. This concept recently acquired a lot of reputation, due not only its mathematical importance, but because the wide range of application in X-ray, crystallography, circuit design, coding theory, astronomy, cryptography, and communication network design. Graph labeling, most graph labeling methods trace their origin to the Rosa in 1967. From 1967 till today, over 200 graph labeling techniques have been studied in thousands of papers. A labeling of graph G is any mapping that sends certain set of graph elements to a certain set of positive integers. If the domain is the vertex set or edge set, then the labeling is called vertex labeling or an edge labeling. If the domain is vertex set union edge set, then the labeling is called total labeling. Under the total labeling, the associate vertex weight of a vertex V is defined as follow. There's two cases. The first case, if we're looking of vertex weight under total labeling will be the labeling of the vertex plus the labeling of all edge incident to that vertex. And for the edge weight under the total labeling, the edge weight will be the labeling of the edge itself and plus the label of two end vertices. Vertex labeling. Graceful labeling. Rosa in 1967 identified beta valuation were later renamed as graceful by Solomon Column. In 1972, in the paper called How to Number a Graph, Graph Theory and Computing, Academic Press, New York, 1972. What is a graceful labeling? Graceful labeling, let graph G with P vertices and the Q edge, a function F, start from set of vertices to the number 0, 1, 2, extra up to the number of edges. Q here represent the number of edges of a graph G. This function is called a beta valuation or graceful if it is one-to-one function such that when each edge is assigned the label, the absolute value of the difference between the labeling of these two vertices, the resulting edge label are distinct integer running from 1 up to the number of edges. Let us take example. Look at this example. Here the graph, first we need to count number of edges. This graph have 12 edges. So for the graceful labeling, now we use numbers from 0 to 12, and this number we use it to labeling the vertices randomly in such way that the absolute value of the difference between two labeling of any two vertices adjacent with edge must be running from 1 up to the number of edges. We will put the 0 in the center, and I put the 12 here down, and 1 here, 9, 2. Now, look at, see what we will get here. We are got this number, 12, 11, 10, 12, 12 minus 0 become 12. 12 minus 1 become 11. 12 minus 2, 10. And the other numbers same. So now we have the numbers from 12 to 7. What is the missing number? 3, 4, 5, 6. 1 and 2 also we have. This is 1 and 2. We have only need 4 number. 3, 4, 5, 6. For 3, 4, I will put 5 here. So I get 3 and 4. For 5 and 6, I will put 6 here. So I get 6 and 5. Now this labeling is a graceful labeling because the edge running from 1 up to number of edges, 1, 2, 3, 4, up to 12. Let's go for another case. Graceful labeling of complete graphs. For the K1, it's very simple. Just put 0 on the circle, that's finish. For the K2, I put 0 and 1. So 1 minus 0 become 1. So this is a graceful labeling. For the K3, also it's easy. Just I put 0, 3, 2. So now I get graceful, 1, 2, 3. K4, similarly, this is a graceful. What about the complete graph greater than K4? For complete graph, like Kn, n greater than or equal 5, till today, there is no graceful labeling. There is no graceful labeling for complete graph, Kn, n greater than or equal 5 till today. Some person prove graceful labeling after giving some condition. They remove some edges from complete graph. After removing some edges, then he can get graceful labeling. But without removing any edge from complete graph, it is not possible to get graceful labeling. from K5 up to Kn. Graceful labeling of trees. A major unproved conjecture in graph theory is the graceful tree conjecture or Ringel conjecture, named after Gerhard Ringel, which hypothesized that all trees are graceful. The Ringel causing conjecture is also known as the graceful labeling conjecture. Causing once called the effort to prove the conjecture disease. Why he said like that? Look at any tree. How many non-isomorphic tree with one vertex? We have only one. Suppose we will go with a tree with 6 vertices. Tree with 6 vertices have 6 non-isomorphic cases. So for every case, the proof is different. But when we go up, suppose we go up with a tree within 10 vertices. Tree within 10 vertices have 106 non-isomorphic cases. And the tree with 25, see the number. So till today, they prove that a tree is up to 36 vertices is graceful because the number of non-isomorphic cases is huge. See, the number is very huge here. Edge labeling. Magic labeling. What is the magic square? Look at this square. We arrange the number in this square. In some cases, if we add the number of any row or any column, the result will be the same. The first row, 4 plus 9 plus 2, 15. Second row, 3 plus 5 plus 7, 15. 8 plus 1 plus 6, 15. What about the column? 4 plus 3 plus 8, 15. 15, 15. This is called magic square. And this is magic square 4 by 4 also. Here the magic constant, here the magic constant will be 34. For all rows and columns, if added the number, that you will get only one number, 34. Magic labeling. Motivation by the notion of magic square in number theory. Magic labeling was introduced by Sathak in 1963. A graph G is said to be magic if its edge can be labeled with distinct positive integer such that for each vertex V, the sum of the labels of the edge incident with V is same for every vertex. Moreover, if the edge label consists of consecutive positive integer, then the labeling is called super magic. Super magic labeling was introduced first by Sathak in 1967. Now, look at this magic square, 3 by 3. We'll transfer this to the graph. This is complete bipartite graph K3, 3. Here, every column will give the labeling for one edge, and every row also give the labeling for one edge. This is U1, U2, U3, U1, U2, U3, and this is V1, V2, V3. This is the V1, V2, V3. So this is, if you look at the graph, this is a magic labeling, complete bipartite graph, K3, 3, and this is the vertex magic edge labeling. All the vertices of this graph, the weights is 15 only. Let us look at another case of a graph. Suppose we look at the path graph, P2. For P2, we have only one edge. So I put the number 1 in the center. Both the weight of the vertex will be 1. So this is magic labeling. It is possible for P2. The kind of magic labeling we're speaking about it now, edge labeling, vertex magic, edge labeling. We're labeling only the edge. Look at the case P3. For P3, I put 1 here, 2. What is the weight of the vertices? 1, 3, 2. So it is not magic. What about P4? If I put 1, 2, 3, also the labeling, the vertices weight is different. So it is not vertex magic labeling. C, for the pathygraph, any pathygraph, it is not possible after P2, it is not possible to get magic labeling from P4 up to Pn. It is not possible to get edge label, vertex magic edge labeling. Why? Because the center number here, this one, it is shared with the weight of this vertex and this vertex. And here we will use numbers different from this. So these two vertices the weight is different. These two vertices have the same weight only if we repeat this number here. So it's not possible for the definition of labeling. So for the pathygraph, it is not possible. After P2, it's not possible to get edge labeling vertex magic. Look at this graph. The pathygraph is very simple and it's not possible to get magic. Look at this graph. This graph, it is not regular graph. The center vertex of degree 4, this is vertex degree 2, this is vertex degree 3. But we will show you that this is possible to get vertex magic. I put here 1, 2, 3. I put here 4 and 5. Now, first check the weight of the center vertex, because there is no more edge to label. For the center vertex, there is no more edge to label. Finish. Check weight of this vertex. 1 plus 4 plus 5 plus 2, it will become 12. Now, to do this graph, vertex magic labeling, this vertex, the weight of this vertex must be 12. This is 12. This is 12. This is 12. To let this vertex, weight of this vertex, to let it be 12, I need to put here 8. And down I put 7. So now this is the weight 12 and this is 12. What about this? 8 plus 3 plus 1 again would be 12. So now this is graph vertex magic edge labeling. This is a graph, is a funny graph. This is funny graph. We got it from wheelie graph after removing one edge. After removing one edge from wheelie graph, we got this graph. This is called funny graph. Edge magic total labeling. Actually, edge labeling, vertex magic edge labeling is very difficult. So another case of magic labeling is as simple as edge magic total labeling. When we go with total labeling, the problem will be easier. The concept of edge magic total labeling has its origin in the work of Coursing and Rosa in 1970 on what they called magic valuation of a graph. And vertex magic total labeling were introduced by Miller, Salman, and others in 2002. Let us take simple example for the edge magic total labeling. We label set of vertices first, and we label set of edge. Now we will check the weight of edges. So the weight of all edges will become here 14. 1 plus 4 plus 9, 14. 4 plus 2 plus 8, 14. 2 plus 5 plus 7, and 5 plus 3 plus 6. So this is called edge magic total labeling of the pathygraph P5. By magic labeling. Another kind of magic labeling is called by magic labeling. The notion of an edge by magic total labeling was introduced by J. Pascal Babuji in 2004 as a generalization of super edge magic total labeling, in which there exist two distinct constants, K1 and K2, such that the edge weights involved in this labeling are either equal to a constant K1 or K2. An edge by magic labeling is of interest for a graph that do not have any super edge magic total labeling. Some graph it is not possible to get magic. So by magic is very important for that graph. And in some cases, if magic is there, by magic also is there. See, look at this graph. This is already, we are showing the last slide. This is edge magic total labeling. The same graph will prove that now it is also edge by magic total labeling. We label set of vertices first, then set of edges. Now we check the weight. Check the weight of the edges. The weight of edge gives two different constants. So this labeling called edge by magic total labeling. Let's go for another case. We label set of vertices and we label set of edge. We'll check the weight of edge. Now for this graph, all the edge connected with the center vertex, the weight is 15. For all edges, the weight is 15. And other edges on the circle, the weight is 16. So this is by magic total, edge by magic total labeling. Face by magic labeling with an application. The notion of face by magic labeling was introduced by Mohammed Ali and J. Bhaskar Babuji in 2016, where they proved that several families of graph admits face by magic labeling. What is the reason we introduced this notion? Because a lot of for those graphs, there is no face magic. So face by magic is important for those graphs. Look at this graph. This is the wheel graph. I label the vertices, edge, and I'll check the weight of the faces. The weight of the faces in the graph give all two distant constants, 47 and 48. So this is face by magic total labeling. Here in this case, we don't need to bother about outer face. Why? Because the outer face is not a three-sided faces. Here, only this three-sided faces. So definition of magic or by magic, for every S-sided faces, they must have the same constant. For every S-sided faces, they must have same constant. For outer faces, different sided faces. So it is not problem for us outer face. Look at this graph. This is a graph called strong face wheel graph. We label set of vertices and set of edges, and we'll check the weight of faces. The weight of faces of this graph have two different constants, 98, 99 for all these faces. Only two constants. We have 98 and 99. So this is face by magic labeling of type 110 for strong face wheel graph. For this graph, we will give some application. What is the application? Encryption. Now we can use the technique of face by magic labeling on strong face wheel graph to encrypt two numbers using the digits of the numbers. We will take two numbers. The first number, S1, is 274011, and the second number, S2, 3050. This is two different numbers. Take this graph. On the left, look at this on the left. This is normal. Sorry. This is normal face by magic labeling of type 110 for strong face wheel graph. Now we have two numbers, S1 and S2. I will encrypt first number S1 in these vertices, outer vertices. And for the second number S2, I will keep it secretly in these vertices. Look, for the edge labeling, I will not disturb. The edge labeling is same for this case. See, the right side and the left side edge labeling is same. What about the vertex labeling? We define the function for encryption. This is function now, define it for encryption for these two numbers, S1 and S2. For S1, I change the labeling for these vertices. How I change it? With this definition. G of Vi equal f of Vi plus n plus 1. N represent here the number of the vertices on the wheel graph. Here, this will graph W6. So N becomes 6 in these cases. Plus DI. What is DI? DI, the digits of the number S1. So D1 will become 2, D2, 7, D3, 4, D6, 1. So let us go for the first vertex. G of Vi equal F of Vi. F of Vi now we have 2 plus N plus 1. N here 6 plus 1, 7. 7 plus 2 is equal 9. Plus Di, first number. What's the first number? 2. 9 plus 2 will become 11. So I put 11 here. Let us go for the second digit, 7. For the same process, F of Vi, 3 plus 7, 10 plus Di, 10 plus 7, 17. Let us go for the fourth number, 4. I keep it here. 4 plus 7, 11. Plus 4 would become 15. Like this way, I will finish other vertices on the outer. Now we finish for a first number, S1. Let us go for the second number, S2. We will give different function for S2. For let us encryption more complex, we will give different function for these two number. S2 difference. G of UI. What is UI? These vertices are called UI. This is U1, U2, U3, U4, U5, U6. So G of UI equal F of UI plus 2N plus EI. For I running from 1 up to N, with the condition if the digit EI is greater than or equal 0. That's mean if the numbers here greater than or equal 0. And G of UI equal F of UI, the same here, the same case here, if the digits is a blank space. What's the blank space? See here, first number have 6 digits, 1, 2, 3, 4, 5, 6. Second number have only 4 digits, 1, 2, 3, 4. So the 5 digits here blank space, the second blank space. So let us $20 plus the first digit. 20 plus 3, 23. I put similarly for other vertices here. Now the digits is over for the second number S2. Those two vertices will leave it as it is, 12 and 13. So look at this graph. We encrypt these two numbers in this graph. So we'll send this graph to some person, and we encrypt this number secretly. The person who will got this graph, he have the procedure for decryption to get this two number. The decryption process will be like this. We in the decryption process, we use the idea of matrix in linear algebra and do some process here. After doing all this process, then finally we will get this matrix. See this matrix. What this matrix? 2, 7, 4, 0, 1, 1. This is the first number, S1. This is the S1. 2, 7, 4, 0, 1, 1. Look at this column. Look at this column. 3, 0, 5, 0, minus 12, minus 13. 3, 0, 5, 0, the second number. The second number, S2. and this is will ignore it. Any number minus will ignore it. That's mean come from the blank space, so we'll ignore it. So the person who will got this graph, he can able to get this two secret number if he get this is the idea of this matrix. Thank you so much for your listening. If there is any question, I am ready.
Hello, sir.
Hello? Yes, I hear
Yes.
you.
Okay, sir. Dear participants, if you have any doubt, kindly ask to our resource person.
Hello?
Yes, sir.
Yes?
Dear participants, if you have any doubt, means kindly ask to sir.
Thank you. I am not hearing you clear. The voice is not clear. Sorry for me.
Okay,
The voice is not clear. Some noise in the voice, so I am unable to hear what you say.
Okay, sir. Now it is clear, sir.
This is not too much.
Okay.
I'd like to thank the Mohammed Sathak College of Engineering to give me a chance for this my talk. Thank you so much for everybody.
Yes, sir. Thank you so much, sir.
Thank you so much, madam.
Thank you, sir.
Thank you.
Dear participants, if you have any doubt, kindly ask to sir.
Yeah, please, if anybody have any doubt, let us know.
Dear participants, if you have any doubt, kindly ask to sir.
Hello, sir.
Yes, welcome, madam. Yes.
I'm Jeffrey. I did my thesis based on graph theory itself. So
Yes.
you explained an application on computer science, encryption, decryption, coding.
Okay.
Is there any other application in other science areas like biology?
For labeling?
Yeah. Yes, sir.
I don't have an idea right now. You want to do some application in another branch, right? You want some application for the labeling, right?
Yes, my topic is weighted graph theory. Means the
weighted graph theory. Weighted graph
yes,
theory.
Sir.
Okay.
Yes,
okay.
Sir. So it have an application in chemical graph theory.
And yes.
In chemistry, it is.
In chemistry?
Yes,
in chemistry?
Yes, sir.
Okay. Let me think for you about some application, and I will send it to you. You can contact me with email. I think some application about this, and I give you some idea later. Okay?
Okay, sir. Thank you.
Welcome, madam. Welcome.
Thank you, ma'am. I will give sir's mail ID. If you have any doubt, you just ask to sir.
Okay, sir. Okay.
Any other participants, if you have any doubt, kindly ask to sir. Okay. Sir?
Yes?
Okay, thank you, sir. Nice presentation.
Thank you so much,
sir.
madam.
You have clearly explained about the magic labeling and everything, sir. Thank you so much, sir.
Thank you so much, madam.
Great
My
presentation
regards to
and
all everybody.
spending your time with us for your good presentation, sir. Thank you.
You are
so
welcome.
Much,
I am happy to give me that chance to give the talk in this university. Thank you so much.
Okay. Thank you so much, sir.
Welcome,
now I call
madam.
upon Satya ma'am to deliver the vote of thanks.
Hello, ma'am. Can you hear my voice?
Yes, ma'am.
Okay. Good evening. Good evening, one and all gathered here on this wonderful evening. I would like to present the vote of thanks. We take this golden opportunity to take the respected chief guest of this FDP, Dr. Mohammed Ali Ahmed, sir, well authorized speech about the graph theory and the labeling with applications. Thank you, sir. I would like to thank our Thank you, sir. I would like to thank our beloved principal, staff members, and all participants, volunteers, and the last but not least, our beloved audience and for making this FTP as a grand success. Once again, I thank one and all present here. Thank you.
Thank you so much, ma'am. Thank you so much.
Thank you.
Sir.
Thank you.
Thank you so much, sir. Thank you, sir.
Thank you, madam.
Okay. Participants, one.
Ma'am,
Sir.
thank you, ma'am. Thank you, ma'am. What
Sir,
about feedback,
you have any
ma'am?
doubt? I already posted, sir.
Okay, the group.
You can
Thank
see
you.
in the chat box, sir. I have posted
Yes, ma'am.
already.
Thank you.
Dear participants, kindly fill your feedback form. It should be considered as attendance for today's FDP. Please fill the feedback. It will be on in up to 5 o'clock only. Kindly fill the feedback form. Thank you so much. Tomorrow we can meet for the day 2 seminar FDP. Thank you so much.
Thank you, madam. Bye.
Thank you, sir. Thank you, sir. Bye, sir.
Thank you, Sam. Thank you.
Thank you.